Hi, in this video we're going to see how we should solve this integral of the integral of 0 to 1 of sine squared ln x over ln squared x with respect to x. So first here I'm going to remind you of the identity of sine squared x, which is 1 minus cosine 2x divided by 2. And if I plug this in for my integral from 0 to 1, it's going to be 1 minus cosine of 2 ln x divided by ln squared x over 2 with respect to x. Now, if I move this half to the outside here, it's going to be 0 to 1, 1 minus cosine of 2 ln x over ln squared x dx. Now, if I find this integral here and divide it by 2, I'm going to find my actual integral. Thus, I'm going to call I of t to be the integral from 0 to 1 of 1 minus cosine of 2 cosine of t ln x divided by ln squared x dx. And if I plug in of I of 2, I'm going to get this integral here. So with Feynman's technique, I'm going to differentiate both sides with respect to t, which is going to be the integral from 0 to 1. This is going to be partial derivative when it's moving to inside this integral. Differentiation under integral is going to be sine t ln x according to the chain rule multiplied by ln x divided by ln squared x dx. Now here, these two ln x's are going to cancel out, and my I prime of t is going to be the integral from 0 to 1 of sine of t ln x divided by ln x dx. Now I want to get rid of this ln x here, thus I'm going to differentiate it once more to get the integral from 0 to 1 of, if I differentiate it once more, it's going to be cosine of t ln x over ln x times a ln x again. Again, these two ln x's are going to cancel out perfectly, and I'm going to be left with I prime prime of t equals to integral from 0 to 1 cosine of t ln x dx. I'm going to write it a little bit better. Cosine of t ln x dx. Here, to solve this integral, now this integral is solvable. To solve this, I'm going to let u be equal to ln x, and my dA thus is going to be 1 over x dx. My dx therefore is x dA, which is, if I use the definition of the logarithm, I'm going to see that x is e to the power of a. Thus dx is e to the power of a dA. So remember the integration by parts u dv is uv minus v du. Here, if I do this and apply the change of bounds, I'm going to get the integral from negative infinity to 0 of cosine ta e to the a dA. And if I write it more cleanly, it's going to be negative infinity to 0 of e to the a cosine ta dA here. So now we're good. So remember the integration by parts that I showed you here. I'm going to say u is e to the a, du is e to the a dA. The u's and a's are looking similar. Let me just correct this. Thus d to the a is du over e to the a. Okay, which is e to the negative a du. So right now, if I do the integration by parts, my I prime prime of t is going to be e to the t sine, oops, I forgot to write my, so my dv first, I'm going to write my dv also, it's going to be cosine of ta, and my v is going to be sine ta over t. My u is going to be e to the a, and du is going to be e to the a dA. So now I can do the integration by parts for the I prime of t, which is uv e to the a sine ta over t negative infinity to 0 minus negative infinity to 0 integral of du e to the a multiplied by v sine ta over t dA. And my I prime prime of t is going to be, this limit is going to go down to 0. So I'm going to be left with, oops, sorry, my stuff fell from my table, really sorry. It's going to be negative 1 over t, the integral from negative infinity to 0 e to the a sine ta dA. If I do the integration by parts again, I'm going to get u equals to e to the a, du is e to the a dA, and dv is sine ta, that's v is negative cosine ta over t, v is negative, let me write it better, cosine of ta over t here. So if I do the integration by parts again, I prime prime of t, it's going to be negative 1 over t times negative e to the a cosine of ta over t, negative infinity to 0 plus 1 over t from negative infinity to 0 e to the a cosine ta dA. These limits, the first limit here is going to go down to negative 1 over t, thus it's negative 1 over t times negative 1 over t plus 1 over t. This integral here is the same as I prime prime of t, thus 1 over t times I prime prime of t. If I expand it, it's going to be plus 1 over t squared minus 1 over t squared I prime prime of t equals to I prime prime of t. Now we have a good equation here. If I collect the I prime of t on one side, plus 1 over t squared I prime prime of t is equal to 1 over t squared. I prime prime of t, therefore, if I factor it out, it's going to be 1 plus 1 over t squared is equal to 1 over t squared. I prime prime of t is 1 over t squared divided by t squared plus 1 over t squared. T squared over t squared plus 1 over t squared. Thus it is 1 over t squared over t squared plus 1 over t squared, which is t squared over t squared times t squared plus 1. These two are going to go away, thus it's going to be 1 over t squared plus 1. I prime prime of t. Does this integral sound familiar to you? Well, if I integrate both sides, I prime prime of t dt and 1 over t squared plus 1 dt, this is the derivative of arctan of x. This is going to be arctan of t plus c, some constant of integration, and it's going to be I prime of t. To determine the constant of integration, we are going to, first I'm going to write I prime of t, which is the integral from 0 to 1 cosine t ln x, sorry, sine sine of t ln x dx is arc tan of t plus c. And if I let t be equals to 0, this side is going to go down to 0, this is going to go down to 0, and c is equal to 0. My I prime of t is arc tan of t. Now I want to integrate this I prime of t with respect to t once more. Arc tan of t dt. The integration of arc tan of t is a little bit harder, but I'm not going to do the whole thing because this video is already so long and I have to do it make a video a lot more longer, which is not so much efficient for YouTube. But I'm going to write the integral antiderivative of arc tan t, which is t arc tan t minus half ln t squared plus 1 plus c some constant of integration. You can find the integral antiderivative of arc tan of t on your own, but I'm not going to do it in this video. Again, if I equate it to the integral from 0 to 1, the I of t of 1 minus cosine t ln x over ln squared x dx is going to be, if I let t be equals to 0, this side is going to go to 0, this is going to go to 0. 1 minus cosine of 0 is 0. Thus, the second constant of integration is also 0. Therefore, my I of t is, hold on, we're almost there, is t arc tan of t minus half ln 1 plus t squared. And I said that if I find I of 2, I have found my integral. Thus, I of 2 here is 2 arc tan of 2 minus half ln of 5. But we're almost there, but we're not done yet. We said that the integral is half of I of 2, our original integral. Original integral is half I of 2. And I have to divide this by 2 to get the result that I want. Thus, I'm going to get I naught to be equal to arc tan of 2 minus 1 over 4 ln of 5. And this is the neat result of this integral. Thus, I can write the integral from 0 to 1 of sine squared ln x divided by ln squared x dx to be arc tan of 2 minus 1 over 4 ln of 5. And this is the very, very, very neat result of my integral solved with the Feynman's technique of integration, which is differentiation under the integral sign. This was probably by far the hardest integral I solved. But anyways, please like and subscribe to my channel. If you have any questions, please let me know in the comments, and I will see you next video.